All right. Hi, everyone. We are PneuSonus, a low-cost acoustic device to target pediatric pneumonia. Now, pneumonia is an infection in the lung that causes inflammation and fluid buildup. And every year in the United States, it's a leading cause of mortality as well as hospitalization of children between the ages of 0 to 5. And of these, 11% are cases of misdiagnosis, delayed treatment, or a failure to identify early symptoms. Finally, pneumonia displays higher incidences by nearly 80% in households of lower socioeconomic status. Now, current medical diagnosis for pneumonia may include an X-ray, a physical exam, or a pulse oximetry test. However, these methods are not very specific, as pneumonia is often confused with asthma. They may also not be the most accessible, given that they can be costly and also require close proximity to a hospital or a clinic, and are also not the most user-friendly, since some of them do require some sort of experience to use and interpret. And with that, I will pass it on to Simi, who will talk more about PneuSonus and our proposed solution.
So these gaps in the current diagnosis mentioned by Kelly is where we identified the unmet need for PneuSonus. So PneuSonus is our end givers, our child caregivers from lower socioeconomic households for which going to the hospital or the doctor is not an easy option. So it detects fluid in the lung, which according to literature is indicative of pneumonia. It's meant to be a way to routinely check for pneumonia at home, and it also outputs a caregiver recommendation on whether or not to seek further medical attention. To get a better understanding as to what PneuSonus looks like, here you can see it is a piece that wraps around the baby's chest, and on the front is a speaker that emits a sound wave, and on the back is a microphone that picks up that sound wave. On our encasement, the user can interface with the device, and the recommendation will also be outputted there. When we were designing PneuSonus, we had 5 main criteria in mind. The first was it had to be portable, so that it could be easily transportable throughout the household as well as other locations as it needed. The second is it had to be affordable for the lower socioeconomic households. We determined a cost of less than $150 because that is about a 50 times reduction from the current diagnostics on the market. The third was it had to be adjustable between the different sizes because our age ranges are from 0 to 5 years old, so it had to adjust to the different chest sizes. The fourth is it had to be user-friendly so that the child caregivers can easily and accurately use our device. And last, it had to be accurate in the detection of healthy versus unhealthy. And we determined a greater than or equal to 85% accuracy rate because this is comparable to current diagnostics on the market. Now Iman will talk more about our device.
Thanks, Simi. So how does PneuSonus actually operate? So after powering the device on from our encased unit, users will see a welcome screen to prompt starting a test. They will place a custom PneuSonus t-shirt on the child and then follow the patches on the front and back to properly place our adjustable strap and align its sensors. Once secure, they can press the labeled run button, prompting a wide frequency range sound called a chirp to play from the speaker in the strap's front through the lungs and collected with the microphone in the back. And the transmitted signal's frequency response is processed with our software, and a recommendation is shown to seek further care based on whether fluid was detected. So in progressing from simple and bulky hardware to our final product, how did we meet our specified goals? So for portability and affordability, we placed our low-cost sensor circuit on a proto board that halved our original casing from our first prototype size. And we charged our entire device with a battery pack that users can easily recharge with a simple USB cable. And these components were assembled with our processing unit in a small 3D printed case with labeled slots, as well as attached via cables to our adjustable strap, which we ensured to be adjustable from the back, shoulder, and chest area, as well as having different sizes for those custom t-shirts to account for our patient's age range. And finally, interfacing a high-resolution display with simple switches with our casing ensured our user experience to be able to indicate and control when the device was powered on, as well as showing results after testing. And so with that, I'll pass it on to Sophia for the software behind processing our data into accurate results.
Thank you, Iman. So just to talk a bit about how we coded this machine learning algorithm, most of our coding was done on Google Colab, given its collaborativity with Google Drive, where most of our trials were stored. And also we used Python due to the fact of the many packages that we could use for machine learning algorithms. And the specific machine learning model we used was a logistic regression model because we wanted to use a classifier model that returned a binary classification, yes or no. And logistic regression is also widely used in the industry for its efficiency and simplicity. So just to run you through a bit about our model pipeline, as mentioned by Iman, the signal is recorded by a microphone, and then this returns a data set, which is then processed into this pipeline. So then the data goes under a rigorous data cleaning and standardization process, which helps remove outliers and potential unwanted frequencies that may have affected, or noise that may have affected our data, as well as variability between the chest distance. Then this data is undergone a frequency selection stage or feature selection. And the reason for doing so is to avoid overfitting of our model. Currently, we have around 4,000 different data points for the frequency spectrum. However, we wanted to narrow that down to avoid our model from overfitting to just those to all of those 4,000 points. Then after this processing, the data is gone through a logistic regression model, which then returns the prediction, and then that prediction is displayed on our user interface. So just to talk a bit more about our results, initially when we first ran our machine learning model, it actually returned a pretty low percentage of accuracy, around 46%. However, when we added this frequency selection stage, it actually boosted up the accuracy rate to around 67%, which is closer to our training data accuracy rate of 73%. This is important because it shows that our machine learning model isn't just overfitting to our training data and is also accommodating for our test data. Then I want to present a bit about the confusion matrices. So on this slide, I just want to point out that most of our data falls in the true positive, true negative slots. However, in our erroneous data trials, we found that there's a tendency to lean towards the false positives in our data set. And ethically speaking, this is slightly better than having a tendency for false negatives. However, obviously, we are aiming to prevent erroneous trials in general. Now I'm going to pass on to Nicole to talk a bit more about our models.
Thank you, Sophia. So in order to determine all the trials and obtain the results that Sophia just mentioned, we need to have an accurate model. Obviously, trusting on our prototype on babies right now would not be a great idea, ethically speaking, safety-wise, all that. So we knew we needed to have three main goals to develop our model. First is clinical translatability, the second being flexibility in terms of severity of illness, as well as age range, and then lastly being accuracy. So in order to do this, we worked hand in hand with our clinical mentor, Joseph McDonough, over at CHOP, and he recommended to use PVA sponges. I know it sounds a little weird, but bear with me. PVA sponges have the same properties as real lungs, same volume content, same density, so using sound with this wave, it actually makes a real big difference. You can see that in other clinical trials that have been used for breathing rate and accuracy, as well as other devices that use PVA sponges for their devices as well. So with that, we had our PVA sponges, which gave us the properties that we wanted, but then we put them into baby care dolls. This seems a little weird, but hang on. So these baby care dolls gave us the look and feel that we needed. We didn't want to just put the microphone speaker on the sponge and be like, this is a lung. No, we put it in a baby care dolls to give us our complete model, which gave us the look and feel and the device properties that we wanted. And then with that, we are presently working with two researchers at the Wolfson Laboratory at CHOP, and they have graciously agreed to give us some of their pigs to do porcine models with this. So pigs, as you can imagine, are very different from infants, but they give us two properties that our complete models don't: breathability and movement. So our complete models don't move and they don't breathe, but these pigs do. So with that, we have seen some really promising trials so far. We hope to increase this in the next coming weeks. With this provides very exciting trials in terms of IRB approval in the potential future, as well as maybe clinical translatability. And to talk about more things of the future, I'm going to pass it on to Kelly.
Thank you, Nicole. Now for future directions beyond the scope of the semester, the first thing is to establish a wireless transfer of data from the strap to the processing unit. Children tend to move around a lot, so of course we want to find a different way, to transfer that data without having the cables in place. Next will be to refine our machine learning model. So as Sophia briefly explained, ML models require thousands of trials to train, which is why next steps would be to, of course, continue getting more trials, but most importantly, connect with industry experts with experience validating ML models with a limited data subset. And then finally, we want to move to the clinical setting. So we did start testing on animals, but of course we want to move on to apply for IRB, as well as initiate volunteer onboarding to start testing NeuSonus on children. And then with that, this whole year has been quite the journey, but we're very thankful for the opportunity to have developed NeuSonus and start changing the way pneumonia or pediatric pneumonia is detected. We are open for questions.
One question. So you mentioned intended for routine at-home use. How have you thought about how often this is going to be needed? Where's the real need in terms of distributing this to families in need?
Yeah, so I think that when we were doing research, one of the things we found that one of the reasons why pneumonia is like the leading cause of death in infants is because it's diagnosed too late. And one of those reasons is because the initial symptoms are very like cold-like or things like that. So it takes too long for parents to take them into the hospital and then to like rule out pneumonia. So the way that we would instruct this is kind of like you get it once your baby is born and you have it in your house, and the second you start hearing them coughing or sneezing, you routinely check for it until hopefully it doesn't tell you that it's pneumonia, there's fluid in the lung, but at least you'll be able to catch it on earlier on.
Great presentation, and I can totally see how this could be applied for, be used by community health workers in rural settings and developing countries where they can, get access, essentially delivering these services to babies and families, and super helpful that it's low cost, portable. I guess two questions. How did you guys, I like the fact that you started off with design parameters and objectives that you want to design around versus going straight into the design. How did you guys, can you talk me through the process of how you guys decided on those design parameters, especially around the weight and the cost? And then second question, or more consideration, have you guys thought about, rather than having this be a standalone device for accuracy, if you add it to existing physical exam methods, does that improve your accuracy to the point where, it's usable, and so you don't necessarily need to have as high level of accuracy on the device itself?
I can answer the first question. So based on the reason why we chose a lot of things, like when I mentioned the less than $150, it's because we said it's a 50 times reduction from taking in your child to the doctor, then having to pay for x-rays, a pulse ox, all of those. And still it was enough for it to be profitable for us. So of course we calculated the cost of how much it would be for us to produce this. And then we said we want to be profitable, but also have it within the margin so that it's affordable for these lower socioeconomic households. It's also a one-time cost. So it's something if you have multiple children or all of these things, it's just one time and then it fits for all of them. And then, so I think that's kind of how we went about each of them. We looked at the current diagnostics and then found where are the gaps in these and how can we improve on them. And then through that, we established our metrics. And then the second one.
Yeah, I think that's actually a great proposition. I think it's something we have considered because given that our device might not be able to reach 100% accuracy as on currently industry uses for diagnosing pneumonia, I think that in our user manual we might consider adding certain physical examinations that can be done at home that they could do additionally with the device just to again increase the accuracy or give them a better idea of having more results from different methods might be more helpful to the person using the device at home.
I love the idea. I was just going to ask, babies come in all sizes. So I was wondering, I think there was a little bit of it's resizable. So I'll ask, have you thought much about growth for the baby and also the person putting it on, the applicability of it? You mentioned shirt. Can you speak a little bit more about that?
Yeah, so one of the main points of ours is it's 0 to 5. So babies grow, their lungs grow as well. So some of the testing that Sophia did showed that wherever you place in the chest, when it grows, we grow with it. And then with the sizes, so we have the baby size, the onesies, and then we move on to t-shirts as well. So those aren't pictured in here, but we also have t-shirts. We bought them from 0 to 5, so they'll be adjustable. And same with the strap, as Iman was mentioning, it's adjustable from the shoulders to the chest. It's adjustable in all the spots to grow with that baby, no matter what size they are, what shape they are. It'll grow with them.
Oh yeah, and to add on, that just the t-shirts have those badges to show where the mics or the mic and the speaker should go, so that gives a guideline as to as they grow, how should you adjust the strap for the person using it.
So first off, great presentation, guys. I thought it was really clear in terms of how you designed the product, how you improved it. One question I have, this is more of a curiosity. Have you talked to parents in terms of what their receptivity might be? Because I imagine, I'm not a parent myself, but I imagine new parents, they get concerned, and if their baby's coughing or shows cold symptoms, it might just take them right to the doctor. So curious if you feel based on any conversations, they would actually use this over, go to the doctor.
So I can say we have a whole data set of parents and we've spoken to, but I do think, as we mentioned, this is the lower socioeconomic households where their first option isn't always going to be to go to the doctor because they know that's very costly for them. Most of these parents are probably working full-time jobs, have multiple kids to take care of. So then taking them to the hospital would be an additional cost that they might be not be willing to like take on if it's just a cough or something simple like that. So this is more of something that our hopes would be to get doctors in a hospital like as soon as a baby's born to recommend it so that they buy it and then they have it in their house. Does that make sense?